So good evening all the participants present here. So today we are having with us Dr. Sonam Gupta from IBM. So we welcome you to our session. Uh, uh, we welcome you to the 6th day of our FDP on deep learning, which is sponsored by E&ICT Academy, MNIT Jaipur, and under Electronics and Information Technology, Ministry of Electronics and Information Technology. So welcome you, ma'am.
Thank you, sir. Thank you, everyone.
So participants, let me just briefly introduce Dr. Sonam. Then we will continue with our session. So currently, Dr. Sonam is associated with IBM, and she is working as a research scientist at IBM Research Lab, where she explores generative models in language, focusing on large language models. Her work addresses key challenges such as mitigating hallucination in LLMs, enhancing the robustness of retrieval augmented generation systems against retrieval failures, and fine-tuning LLMs while preserving their generalization capabilities. Dr. Sonam holds a PhD from IIT Madras, where she is specialized in computer vision with an emphasis on generative models. Her doctoral research focused on video generation models and video representation, and she has authored multiple publications in leading conferences and workshops, including VMVC, TMLR, CBPR, and NACL. She has also contributed to the research community by serving as a reviewer for prominent conferences and journals such as NeurIPS, ACL, TMLR, and BMVC. Driven by the goal of advancing the practical applications of generative models, Dr. Sonam is committed to making AI system more reliable and robust. So I hope today's session will be very much interesting to all the participants, where we are going to explore the very emerging topics. So without any further delay, I would like to hand over the session to Dr. Sonam. So welcome you, ma'am. We, along with Dr. Surendra Hans, welcome you to our session.
Thank you, sir. Thank you, everybody, for making time to attend this seminar. So today I will be covering details about two important models, BERT and GPT. So let me just start sharing my screen first. So is my screen visible?
Not yet, ma'am.
Okay. Now?
Now it is loading.
Okay.
Yes, now it is visual.
Okay, sure. Thank you. Okay. So today we will be discussing two important topics, BERT and GPT. Specifically, we will discuss about GPT-2 model. So this is the quick outline of the talk. First, so I understand that in the first session today, you have gone through transformer architecture and its details. So that is what would make it easy to follow what happens with BERT and GPT, because they are adaptations of transformer architecture. Their main contribution is not the architecture itself. It's more in the training methodology that they have adopted and the way they have formulated this problem of language understanding and language modeling. So we will be so that's why, but in just to be just to ensure that all of us are on the same page, and I'll have a very quick recap, very high level overview of transformer architecture. Following that, I'll discuss the motivation for both BERT and GPT kind of models. And then we will look into details, GPT models, GPT and GPT-2 and BERT model. So if you have any questions, please feel free to stop me and ask me in middle also. That's okay. Like, is that the format that we are following?
There is no restriction on that one, but they cannot directly interact.
Okay, so
They will
maybe they
put
can post in
their
the
query
chat.
or any out
Okay.
in the chat box only. So yes, parallelly they can.
Okay, sure. Thank you. So you would have seen that we know that transformer contains two main blocks. One is the encoder block and the other is the decoder block, right? So the original transformer, initially like the transformer architecture was proposed in the paper called Attention is All You Need. And there it was proposed for the task of machine translation, right? So suppose you have an input, which is which is in another language like French here. Then what we want to do is we'll pass it through the encoder layers of the transformer architecture. The role of this encoder layer is to learn a contextual representation for each of the words or tokens which are given in the input, right? So right now, for example, this encoder is taking, let's assume that these three words are the three tokens that the encoder takes as the input. Then at the output, we again get three representations corresponding to these three tokens. And those representations would be contextualized. So by contextualized, we mean that it will be aware of the other tokens which are present in the input, right? And then along with this final layer representation, these representations from the encoder networks are fed into the decoder network. And then it starts to generate the translation, right? So for instance, it will generate a translation like, I am a student, right? So this is just one layer, going one layer deep into this encoders and decoders block that I have shown here. So this encoder block, it is not a single block like we know. It is made up of multiple encoder submodules. And the output of the final module is what is being fed to each of the decoder modules. And if we zoom into each of these encoder and decoder modules further, so we will see that at the core of it, the encoder block consists of two important blocks or two important layers. The self-attention layer, which is responsible for learning how much attention is required to be paid to different tokens which are present in the input, followed by a feed-forward layer, right? Which is a fully connected, two fully connected layers, right? We will have this up projection matrix and a down projection matrix. And then, so this itself corresponds to one encoder here. And then we will have multiple such encoders stacked on top of each other. And in the decoder, the overall architecture is almost the similar, with the exception that here we have this encoder decoder attention, or as you also know it, this is also called as cross attention layer, right? So the reason this is called a cross attention layer is because unlike encoder, where the self attention is attending to itself, here the attention is paid to the these representations which we are receiving from this encoder module, right? So that's why this is called as cross attention or encoder decoder attention. So with this background, so if we further enlarge these encoder and decoder blocks here or submodules here, so we will see that, so I have skipped in the previous in the previous representation, I had skipped these fine details like after each self-attention layer, we will also have a residual connection followed by layer normalization, right? And similarly, we'll again have this residual connection and layer normalization after these feed-forward layers for both encoders as well as decoder blocks, right? So now, if we look into it, so the original transformer architecture, it was proposed for the task of machine translation, right? Now, what if we want to use this model for some other tasks, like say sentiment classification? So sentiment classification here, the task is that you are given an input sentence. So for example, the sentence is, wow, India has won the World Cup, right? So here it's a classification task, and it's a two-class classification task. So the output could be a positive sentiment or a negative sentiment, right? Sometimes people also model it as a three-class classification where it can also be a neutral sentence. But usually, let's look into positive and negative sentiments only. So, for example, this sentence like, wow, India has won the World Cup, this is a positive sentiment, right? Now, for humans, it is really easy to learn this task, right? Like, I need not have a lot of examples to, I don't require to use a lot of examples to teach a human that, okay, this is a positive sentiment or this is a negative sentiment. If you understand, if you, me, or somebody else understands the language, then maybe with just a few examples, they would be easily able to understand what this task is, right? So currently, with the given architecture now, the transformer architecture that we saw previously, if we want to use the same model for, say, sentiment classification task, what we can do is we can collect a lot of labeled data, right? So this labeled data would look like, for we will have, say, some 10,000 sentences or 20,000 sentences, and belonging to both the classes, positive sentiment as well as negative sentiment. And for each sentiment, we'll have the corresponding label information. And then we can train using that data set, right? So basically, we can collect labeled data and then train for each task individually. Now, if another task comes up, we'll have to again train this model from scratch. And the cost of training from scratch is not just like the computational cost. There is also a cost associated with collecting this good quality labeled data, right? So those are the two, that is one of the major issues, right, of this approach, that how can we get so much labeled data, right? So the motivation behind this BERT and GPT models was, or has been, that can we reduce the quantity of this labeled data that is required, right? So can we instead use unlabeled data? So the answer is indeed yes, we can use unlabeled data. But then the question comes, how do we use this unlabeled data? So first of all, where is this unlabeled data available? So we all know that at least in today's world, it is digitally available, a lot of free data is available, right? We have a lot of news articles, books, and Wikipedia, and there can be several other sources like that. Like earlier, it used to be Twitter tweets. So like that, there is a lot of unlabeled data. And so this data does not have any labels or any annotations associated with it. So how can we use that? So that's what we will see. So that's what I consider to be the main contributions of these BERT and GPT models. Like, they have proposed how can we leverage such huge amount of unlabeled data. So so the idea is that we can carry out our training in two phases. The first train would be to use this unlabeled data to ensure that the model is able to understand the language, like just like how a kid learns, right? So when a kid is growing up, he or she initially listens to a lot of conversations, a lot of maybe poems or content from the television, internet, and they learn speech, right, in various formats, say in Hindi as well as in English. In general, I'm talking, it can be any other language as well, right? Whatever is their native language. And then they eventually end up picking the language. And once they have the understanding of the language, it becomes really easy to teach them a new concept, right? They don't need formal education for everything. Like for tasks like sentiment classification, after a certain age, they are mature enough to understand that, okay, this is how this sentence would be a positive sentence or a negative sentence. This is what GPT models have proposed, and this is also known as language modeling, or in this case, causal language modeling. So, what is a language model? I think this is something that also you would have seen. So, when we are saying that we are learning a language model, or when we are modeling a language, so in terms of deep learning models, what we essentially learn is we learn a joint distribution over tokens. So x1, x2, x3 to xt here are some tokens taken from a vocabulary, and the joint probability distribution, joint probability of this uh, is my language model. So basically, how can we compute this? So we can use the chain rule. So if we know the probability. Using chain rule, this can be broken down into P of x1 times P of x2 given x1. So that is the likelihood or probability of second occurrence of second token given the first token times the probability of occurrence of third token given the first and the second, right? So in this way, we can, if we learn a model which can predict the next token, right? So the motivation or the intuition here is that suppose if you have a deep learning network which can predict the next token, right? So if you look at each term here, what we are doing essentially is given some input tokens, we are trying to predict the next token. So if we have a model that can predict the next token, then it's not proven, but this is like an intuitive understanding that I'm sharing with you so that you can understand why are we even doing this next token prediction. So then the model would be able to understand the language, right? So otherwise, like how can it know what would the next token be, right? So this is what the architecture proposed by this GPT paper has used. So this GPT paper, it came in 2018 and it was proposed by OpenAI. So the architecture was built on transformers decoder modules. So if you would have also heard, this is a decoder only kind of an architecture. So like I'm saying that this is a decoder kind of an architecture, or this is decoder only model. So what that means is that we do not have, first of all, this model. So what they have done is they started with the transformer architecture, but they decided not to use the encoder part because they just want to learn this task of predicting the next token. So they just want the model to, first of all, learn a language, right? So there is no input to be encoded as such. So there is no encoder in the architecture that is proposed in this GPT paper. So there is no encoder. Then since now we do not have any encoder, right? So we should also remove this cross attention or encoder decoder attention layer, right? Because it doesn't make sense. We don't have this input which was coming here. So that's why they also remove this encoder decoder attention. And finally, this is how the architecture looks like. So this is an abstract representation for the decoder only architecture or the GPT architecture. So it has only these decoder blocks, and each decoder block now contains only masked self attention and the feed forward neural network. So the traditional transformer architecture has the cross attention layer also. So the only difference is that here now there is no cross attention layer because there is no encoder, right? So there are no outputs which are coming from encoder as input to these layers, right? So this is how, so just this itself is the architecture for the GPT model, right? So now, one thing that I want you to pay attention to is that this is not just a self-attention layer, it is a masked self-attention layer, right? So like in the traditional transformer, we were using a masked self-attention. Here also we continue using the masked self-attention. So by masked self-attention, we mean that for computing the representation of a token, in traditional self attention, the model attends to all the other tokens including itself which are present in the input, right? Here this is conditioned only on the tokens which it has previously seen, right? Because if we will show it the tokens which occur after this token, then it will so during inference, when we want to use this model, we want it to do this task of predicting the next token, right? So if we are showing it beforehand during training, because these tokens are available to us, it is cheating in some sense, right? So the model may end up learning some spurious patterns, and it may learn to cheat to look into this and just copy this, which we don't want. So that's why we just attend to the tokens which it has seen previously, right? Coming to, so the architecture wise, I think it is very simple. So coming to the details of the GPT model. So this is, I'm talking about the very first GPT model that came in. So it used 12 decoder layers. Those 12 decoder blocks were there in the architecture, and the embedding dimensions that they have used is 768. and they had used 12 attention heads. And this accounts for a total of 117 million parameter model. So this was a huge model compared to the models which were proposed at the time. And then the training set that they have used for this is they have used a data set called book corpus, which contains 7,000 books from different domains. And they have also shown that, so this is what was the this is what was the pre-training phase, right? So like I said, the main contribution is that, so the GPT paper said that instead of directly fine-tuning for the task, let's do this, or sorry, instead of directly training for a particular task, let's do the training in two phases. So the first phase was pre-training, which is what we were seeing, right? So for pre-training, they just trained the network to predict the next token, right? And then once like the expected outcome of this pre-training is that the network will now have understanding of language. It would have learned the language that it would have seen in the pre-training data. And now we would need a very small subset of supervised fine-tuning data to fine-tune the model for a specific task. So that's what they have shown here. So this diagram is directly taken from the paper. So here they are showing that how can we adapt this pre-trained architecture. So you can see that here they have just masked multi. So this multi stands for multi-headed self-attention, right? They are using 12 heads. So how they have used this masked multi-headed self-attention, 12 such blocks are there. And once this network is pre-trained, we can freeze this layers, and then to adapt it for say task of classification, what they do is whatever is the input sentence, like in our case it was wow, India has won the World Cup, they append specific tokens like start token, and then they use this word extract here to end, and then pass this as the input to the so these blue ones here are the special tokens, right, which they are appending to the input, and then they give this to the transformer. And then at the end of the transformer, if you want to do a classification task, you'll append a linear layer which will map it to the number of classes, right? So you'll have a linear layer followed by application of softmax, and it will give you a one hot vector embedding for the class to which this particular sentence belongs, right? And then you can further fine tune this model. So even during fine tuning, it is up to you whether you want to fine tune only this linear layer or you want to fine tune the entire network, right? So there can be two options. One can decide to keep all of these layers frozen. I think this is something that you would have seen in, so I also saw that you have studied CNN. So in BGG kind of architectures and other architectures, right, where we freeze the entire backbone and then just train the last layer of the architecture, right? So it is up to you, either you want to just train the final layer or you want to train all of the layers which are there in the network, right? So now, so this is what they did for GPT, right? And then in 2019, what they did was they kind of scaled up this GPT model a lot. So GPT-2 in terms of architecture, it is the same, exact same architecture, those decoder blocks stacked one above the other. And the pre-training task is still the next token prediction task. And then you can, once the model is pre-trained, you can fine tune it for your task. And the hope is that because the model now already understands the language, the amount of training data, labeled training data that is required for fine tuning would be much lesser compared to if you what you would have needed if you would have trained the model from scratch, right? So what they did was they directly scaled this model up in terms of both the number of parameters and the amount of training data that was used to train the model, right? So for training data, what they did was there was no high quality large scale data that was available. So one of their main contributions is that they built a new training corpus called as web text, and for building this they scraped the Reddit post and then did some data sanitization and processing. So they ended up scraping like after processing, they ended up having 40 GBs of data to train their network. And also one more thing that I should mention is like how would you build this data, right? So suppose you have a document which contains 10,000 words, right? So what they did was, and now you want to use this for your pre-training your model. So what you can do is, initially even they were doing that, you will divide it into chunks or paragraphs of 512 tokens, of length 512 tokens. And then each sample here becomes your input, right? So for example, suppose if this is the sentence, this 2 lines itself is what I want to use to pre-train my network. If this is what I want to use, what we can do is we'll have sorry. So we'll have it was, suppose, so one of the training examples would be it was released. This would be our input. And now the network should predict in. Likewise, it was released in can be another input, and the network is responsible for predicting 2019. So the context length or the number of tokens, maximum number of tokens, which was there in a sentence was 512 when they were doing this pre-training. So for GPT-2, what they did was they proposed 4 models with different parameters. And here are the details. So the smallest model that they had proposed contained 117 billion parameters. So this was the original GPT model itself. Then they went up, like I said, they scaled it up both in terms of number of parameters and training data. So they appended more number of layers, right? So from 12 layers, they stacked, instead of 12 layers, they stacked 24 layers. Then they went ahead further and stacked 36 layers. And finally, the best performance that they got was after stacking 48 layers, right? And notice that they were not just increasing the number of layers, they were also changing the embedding dimension or the hidden dimension that was used. And they scaled it up from 768 to 1600. And this resulted in, this is like a 1.5 billion parameter model. And this is still GPT-2 architecture, right? And we know ChatGPT was built on top of GPT-3, which was 170 billion parameter model. So that is at a different scale altogether. But unfortunately, that is closed await. So we don't have much information about it. So these are some of the, so one of the interesting things that came out of this GPT-2 models is that of zero-shot learning. So what they also showed is that um, so as the name suggests, right, zero-shot learning. So earlier I was saying that once the model understands the language, we can train it further on a specific task using some labeled data set, right? So, but they showed that even in the absence of any data, uh, like just as it is out of the box, if we pose the problem as a generative problem, right? So for example, if you want to do summarization, right? So you'll give your input and then you just put something like summarize. So, or summary, colon. So then the network should understand, right? What should be the meaningful output after that? So the meaningful output after summary colon should be the summary of the input that the model has seen so far, right? That is something that it should have learned. And indeed, that was the case. So here they tried it with 8 different tasks. And I'm showing the results for 4 different tasks taken from their paper. So they have shown that how this zero shot task performance improved, and it performed comparable or even better in some cases compared to the state of the art models when the number of parameters were increased, right? So here the x-axis contains the number of parameters. So we saw that they have trained 4 different variants of GPT-2 model containing 107 million, 345 million, 762 million, and 1.5 billion parameters. And then on the y-axis, they are reporting the metric that is used to evaluate the quality of that task. And this is the task itself, right? And and this is the task itself. So here you can see that as the number of parameters are increasing, the model starts to perform better and better, right? So like this is what you like, I think this is one of the very important observations or key takeaway, that as we scale the zero shot performance, right? So this is really great. You don't need any labeling to be done at all, and still for example, for reading comprehension task, the model, even without fine tuning for that task, is able to achieve 55% F1 score, right? This is, I think, uh, 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 what they built on for their GPT-3 series of architecture, right? They scaled it even further, and then it did wonders. So this is what happened with the GPT architecture. And now, parallel to this, I would say GPT, the first paper, GPT, which came out in 2018, parallel to this, Google was building its own model, which shares the same motivation of having this two-stage training. First is pre-training, followed by fine-tuning on the given task. So BERT is, uh, as the name suggests, it stands for bidirectional encoder representation from transformers. So here as opposed to, like, we saw that GPT was a decoder only model, BERT is an encoder only model, right? So it just uses the encoder part of the transformer architecture. And we'll see why it does that. Again, here, BERT also used a lot of large unlabeled corpus to pre-train the model, right? The only difference is that instead of using decoder blocks from the transformer architecture, BERT chose to use the encoder blocks. And also because of that, the pre-training task, like for GPT, the pre-training task was next token prediction. So here the pre-training task was different. So using a BERT used a bidirectional approach. So like I said, for GPT, we were using this masked self-attention, right? Which ensured that at any given point, whenever the model is predicting the next token, it is just conditioned on the previous tokens or the tokens that the model has seen so far. Versus in case of BERT, they assume that everything is independent, so they just they look at both the context which occurs before a given token and the tokens which appears after a given token. So I will get into the details of that. I'll show you the exact architecture that they have used. So but BERT is an encoder only model, right? And because it is an encoder only model, just a reminder, so the encoder block has only two main layers that we have seen, the self-attention layer and the feed-forward neural network layer, right? So this is one encoder block, and likewise, they stacked up multiple encoder blocks to come up with the entire architecture. So even in the case of BERT, they have proposed two variants of the BERT model, BERT base and BERT large, right? So BERT base was comparable to GPT in size, and BERT. So if we want to compare BERT and GPT, we should compare using this BERT base model, and the BERT large model has twice the number of parameters compared to the base model, right? As you can see here, BERT base stacked these 12 encoder layers, whereas BERT large stacked 24 encoder layers. And so, like I said, BERT's pre-training task was different, right? So let me just motivate the pre-training task that the BERT is using. So BERT's main aim was to learn representations of the input really well. So instead of focusing on the output more, they wanted to focus on the input itself much more than the output, right? So for example, for a task like sentence classification, right, it's really important to understand the input better in order to correctly predict what the sentiment is. So BERT wanted to do that. So they have used two pre-training tasks. First is masked language modeling, and the second one is next sentence prediction. So in masked language modeling, like the name suggests, what they do is So you'll take the input text, unlabeled input text that you have, and then you will randomly mask 15%, like that's what they have chosen. Empirically, they found it to work the best. But what you will do is you will mask some of the tokens randomly, right? So suppose if this itself is my sentence, Bert's task is to predict the masked words. So instead of task in the input, you will use a special token, say like mask. So you will use a mask here, you will use a mask here. So randomly, every time in the input, you will mask 15% of the token, right? So you will take a sentence or few sentences as input, and out of those sentences, 15% of the tokens would be masked. And then the task, the pre-training tasks that the network has now is to predict what is the most probable word which should come at that masked token space, right? So like one more thing, the masking that we are talking about here is different than the mask that we were looking at the time of GPT, right? Or the mask that we use in the decoder layer. Because in the decoder layer, we don't want to attend on those tokens at all, right? The tokens which occur after the current token, like the future tokens, we don't want to attend to those at all. So that's why we want to make their attention weights equal to 0, right? And for that, I think you would have seen that we add this mask containing -50, -infinity, just to ensure that the attention weights corresponding to those tokens become 0. But unlike that, here, for this mask token, we want the network to attend to the tokens which are occurring before it and the tokens which occur after it. So that's why here we don't do any such thing. So that masking is not applied. Here by masking, it means that we just use a special token. The special token that they have used is something like this, mask. And we just replace all the words which we want to drop with this mask token, right? And this is how exactly like they have used it. So what they do is just having encoder layers would give us representation for all the tokens, right? So they add a classification layer after the output layer in the encoder architecture, in this in the last encode after the last encoder layer. And then for each token, for each mask token, they want to predict which is the most probable token from the vocabulary, right? So these are the details just for that. So the first task that we saw was masked language modeling, right? So this is also called as masked language modeling because we are literally masking some of the tokens, and then the model is responsible for predicting the values corresponding to those tokens. The second task that they have used is called next sentence prediction. So what may happen is that now suppose if you want to fine tune your model, you did BERT pre-training using just that masked language modeling task, right? So there, if you will notice, the tokens are sort of independent of each other, right? Like the model is not getting the notion of a sentence that well. So if we want to use it for tasks like question and answering, we also want to model the model to learn how one sentence is related to the other sentences which may occur in the input. So for that, what they do is they also propose to use this task, next sentence prediction. So the task is very simple. So here, the input would the input would consist of exactly two sentences. So for example, Paul went shopping and he bought a new shirt, right? So the task is just that whether the next sentence is something that should follow the previous sentence, right? So this first case is the example where this is correct. And the second one is the example of an incorrect pair. So given two input sentences, the model needs to predict whether it is correct or whether it is incorrect, right? So for example, Ramona made coffee and vanilla ice cream cones for sale, right? So you can clearly see a incoherent thing here, right? Like these sentences are not coherent. So that's what we want the model to learn. And to construct such examples, given a huge corpus, what we can do is, given a paragraph, we'll pick one sentence and then we'll pick the second sentence from, say, another paragraph or a little far away from this sentence in the whole document, right? And we'll just append that to build the incorrect sentence pair. And for building the correct sentence pair, we can choose any two consecutive sentence pairs from the corpus, right? And for training this, what they do was they take 50% data of each type. So there are 50% examples where they have this combination of correct sentence pair, and there are other 50% samples do not have this correct sentence pair relationship. So the training corpus has equal distribution of both type of samples. And then to ensure that, now this is like a classification task, right? So what they do is they append a special token called as CLS token in the beginning of each input. So now, given these two sentences, they'll append a token called as CLS token in the beginning of the first sentence, and they will have a separator token at the end of each sentence, because the model needs to learn where first sentence has ended and the second sentence is beginning. To clearly demarcate that, they have proposed to use another special token, which they are calling SEP. This stands for separator, right? And then they also include, like for the input, we have positional embedding and word embedding or token embeddings. They also include sentence embedding, indicating whether it is first sentence or the second sentence, that is sentence A or sentence B, and add that to the existing embeddings for each token, right? And in the end, they just use this representation of the CLS token to classify whether it is a correct sentence pair or an incorrect sentence pair. So coming to the details of the BERT architecture, this is something that we have seen. They have proposed two variants, BERT base and BERT large. BERT base consisted of 12 layers and BERT large consisted of 24 layers. With BERT large model, they increase the hidden dimension or the embedding dimension from 768 to 1024, and they also increase the number of attention heads, right? So their model size increased from 110 million parameters to 340 million parameters. So now how can we use this BERT model, right? So to use this BERT model, like I was saying, so this is the first step. This is the pre-training stage, which is also called as semi-supervised training, because here, as you can see, we have we are sort of generating these labels on our own, right? We are taking completely unannotated or unlabeled data, and then we are coming up with this fictitious tasks. Like in case of GPT, it was next token prediction, and in case of BERT, we are randomly replacing some tokens with masks, and we expect the model to predict those masks, right? So like here it is nicely written. So the model is trained on a certain task that enables it to grasp patterns in the language, right? And by the end of the training process, we assume that, or we hope that, the model has the language processing capabilities which is required, or which will make it easier for the model to pick up these specific downstream tasks like like sentiment classification or question answering. In the pre-training stage, we started with the BERT model. We used some openly available text data like Wikipedia data and book corpus, and trained this model for this masked language modeling task. Now in stage 2, because here, if you will notice at the end, now what we get is a model which can learn good representations of the input sentence, right? Also, it is an encoder only model. So what we do is we can further append more layers to this to this pre-trained model, and then train it on the specific task using the labeled data set. So for example, here they are showing that the model is getting trained for the task of detecting whether a given email is spam or not spam, right? So suppose you have a labeled data set like this, like you have some email messages and corresponding to that you have the class information, class labels. Then you can append a linear layer on top of these BERT representation. So usually for classification task, we take the representation of that CLS token, and then you predict whether it is spam or not spam. So there are two ways in which we can use BERT for downstream task. So the first one is we can use it as a feature extractor, right? So in this, what we will do is we will feed our input email. So for example, buy these pills, right? This will be fed as input to the BERT. And whatever representation we get here, that representation, so at the end, we will get some representation for this message, right? So that becomes our feature vector. And now we can take this feature vector to any existing machine learning classification model like KNN or even feed forward neural networks or SVM, right? So for any machine learning traditional classifier, we can use instead of using some one-hot embedding or these basic embeddings that we would have obtained at the initial layer, we can use these features because these are now more enhanced representation of the input and build any normal classifier on top of it. That is one way. So in this scenario, we can use it as a feature extractor, right? The other way is what we do with transfer learning kind of approaches. So we can append more layers to this existing network, and then we can further fine tune it. And here again, during the fine tuning phase, we have an option whether we want to do full fine tuning. That is, we want to fine tune all the layers of the BERT network itself, or we want to keep this frozen and just train last few layers, right? So that is up to us. So this is the overall, this is a broad overview of how BERT and GPT models are different and how they are used. So if you have any questions, like we can. So Vikas sir, I think, yeah, that's it from my side. So if there are any questions, I can answer that, or maybe if there are no questions, we can join again for the hands-on session in some time.
Participants, if there is any question, please go ahead and ask your doubts.
So if you are having any query, you may just ask. Else, we will proceed with the next session after a few minutes. So, anyone? Okay. So I think no question or query from participant side. So I think this session is completed, Matt.
Yes, this session is completed.
Okay. So we may start with the next session that is scheduled from, I think it is from 6:15.
Yes.
So either we may continue this one, or we may join back and start with that one from that time.
Okay, maybe let's start with that. Then at 6:15 p.m., let's join again and start.
Okay, ma'am. Sure, ma'am. Okay.
Yeah,
So
sure.
participants, if you don't have any question, so we will start with the next session at 6:15 only. Meanwhile, just go through the concept, and if you feel to have to ask some query, definitely you can put it in the chat box. And thank you all. Thank you, ma'am. So we will join back at 6:15.
Thank you, everyone.